This is 4.4. We're discussing counting rules, and the first and foremost one is the fundamental counting theorem. And I know you can read it up there for about the number of possibilities and multiplying together, but let's just show you the example I have here. Carson has 2 pair of pants, 4 shirts, and 3 ties. How many different outfits can be worn? Disregarding fashion statements and all that jazz, just how many different ways could he get dressed and leave the house? Well, I made a tree diagram that shows the sample space. 1A blue, 2B green, 2C red, the different combinations. But nobody wants to do that for a large, complex problem. So the idea is this: 2 pair of pants, 4 different shirts, 3 different ties. If you multiply your possibilities together, 2 possible pants, 4 possible shirts, 3 possible ties, you will get 24 different outfits. This is essentially our fundamental counting theorem. It's used in many different ways, as we will see in the future. Next, I start with the word humpback. It has 8 letters. I'd love to know how many ways we could rearrange those letters using all of them, okay? Doesn't have to make sense. The words don't have to make words that make sense or have a definition. But how many ways could we rearrange them? Now in humpback, I would have 8 ways of choosing the first letter. Then I would have 7 ways of choosing the second letter, 6 ways of choosing the third letter, and so on and so forth, until I got down to just 1 letter at the last. Okay? If you multiply those, the counting theorem, multiply those all together, that's what we consider to be called factorial. 8 factorial is 8 times 7 times 6, 5, 4, 3, 2, 1. 8, and it has the little exclamation point next to it. 8 factorial. If you do that with the calculator, 8 factorial, you'll get 40,320. And you're done. With that said, the word hijack also has 8 letters. So it would stand to reason we would have 8 factorial on that one as well. However, the repetition on the 2 letter H's, they're indistinguishable between the 2 of them. So we would need to take the 8 factorial and divide that by the number of repetitions, in this case 2 factorial. And if you take 8 factorial, which we know to be 40,320, and divide it by 2 factorial, 2 times 1 is 2, we would end up with an answer that is 20,160. The rule for that basically looks like this. N factorial, the 8 factorial on top, and then N1, N2, N3, and N4 factorials are all the possible repetitions. So, another set of examples here. I have the word jumpingly. It's 9 letters long. I do not have any repetition. So it would actually just be 9 factorial. 9 times 8 times 7, 6, 5, 4, 3, 2, 1, which would give us 362,880 ways to use all 9 letters in the word jumpingly. However, what if I had the word paparazzi? Paparazzi also has 9 letters in it. The problem there is, when you take your 9 factorial, you then have to divide by everything that has a repetition. I have 2 P's, that's a 2 factorial. I have 2 Z's, that's a 2 factorial. And I actually have 1, 2, 3 letter A's, that's a 3 factorial. So while that top is going to be 362,880, my denominator is going to be made up of 2 factorial, which is 2 times 1, 2 factorial, which is 2 times 1, and 3 factorial, which is 3 times 2 times 1. That's 6 times 2 is 12, times 2 is 24. Using the calculator at this point, we would end up with a grand total of 15,120 ways to write the letters in the word paparazzi. Done. But let's say we didn't want to use all the letters. Here's a word, short word, desk. Maybe I only want to pick out pairs of letters, like DE, or S and E, or K and D, or SK. Well, if I write down all my possibilities, they would look like this. No one wants to do that. That's a lot of work. So the idea would be, if we're only choosing 2 letters, I have 4 ways of choosing the first letter, and I have 3 ways of choosing the second letter. 4 times 3, 12. Notice that's exactly what I have here. I have 12 ways. And I'm finished with that one. Now this gets me a little bit more of a challenge when we get into the next topic, and I'll show you what I mean. We have this thing called permutations and another topic called combinations. Let's start with permutations. Permutations are when you do not have, where'd it go? The order does matter. The order matters. So let's just say, for example, there's 60 people. Okay? There are 60 people in the balloon fan club, right? Balloon fan club. If I am looking for 3 officers, a president, a vice president, and a secretary. A president, a vice president, and a secretary. The order of the people I choose matters because they each have an individual job. Okay, so, you know, Tom, Lisa, and Jeremy, Tom the president, Lisa the vice president, Jeremy the secretary, is not the same as Lisa the president, Jeremy the vice president, and John being the president. They're not the same. The order here matters. In which case we're looking for what's called permutations. So I would be asking you for 60 permutations of 3. This has with it a specific formula. And it says that we would take 60 permutations of 3 would be 60 factorial on top, and then 60 minus 3 quantity factorial on the bottom, or 60 factorial over 57 factorial. Using the calculator, that number would come out to be 205,320 permutations. That's how many different ways I could choose a president, vice president, and secretary. And the order would matter. Now sometimes the order isn't going to matter for us. For example, let's say we still have the 60 fan club, right? Still have this 60-person fan club as well. But I ask for 3 volunteers to go do a task. I don't care if it's, you know, Peter, Paul, and Mary, or Mary, Peter, and Paul, or Paul and Peter and Mary. The order does not matter in this case. It's just 3 people creating a task or doing a task. If that is the case, and the order does not matter, we follow a slightly different formula. These are now called combinations. 60 people in the fan club, and you're choosing or making combinations of 3. When the order does not matter, we would have our 60 factorial on top. We would still have the 60 minus 3 factorial on the bottom, but then we also have to account for 3 factorial on the denominator as well, because we have to divide out the repetition of the same 3 people going in the group. So you use the calculator, 60 factorial divided by, and I guess that's what, 3 times 2 times 1 times 57 factorial. You use the calculator. This answer comes all the way out to 34,220. And you're done. So when the order matters, you use permutations. When the order does not matter, you use combinations. I have some things for you to try. Page 235, 3 to 16, all. Thank you.